Hi, in this video, I want to show you how to use position versus time graphs. Let's start with an example. Albert walked 3 meters in 3 seconds and stopped to chat with his friend Isaac for 5 seconds. Then, Isaac told Albert that he has the COVID, and Albert turned and sprinted 12 meters in 3 seconds in the opposite direction. He then stopped for a rest. So, position versus time graphs are really helpful because they help show a motion, show how an object is moving over time. So we're starting at a position of 0 for Albert. This line shows Albert's motion in the first 3 seconds. He goes 3 meters. And then he stops for 5 seconds. And then he sprints in the opposite direction and then stops again. So this is a very helpful tool, but it's more helpful than it appears because if you look closely at this and you only had the graph, you would actually be able to calculate Albert's velocity, his average velocity over each branch or each leg of his journey. So for example, in this first leg of his journey, he goes a distance of 3 meters and it takes him 3 seconds. And so we can find his average velocity over this first 3 seconds is a positive 3 change in his position divided by 3 seconds. So that would be 3 divided by 3, 1 meter per second. Sorry if you have trouble seeing that. You can also calculate his velocity here if you didn't know any of this information. The position is remaining at 3 meters for a total of 5 seconds. And so the average velocity here, written as an equation, his change in position is from 3 to 3. That's no change. And so we write 0 over 5 seconds. So his average velocity is 0 for this leg of the journey. We can do the same thing down here, and this is a bigger drop. And we're told, and we could count this, right? He goes from 3 to 9. So that's 3 down to negative 9. That's a jump of a displacement of negative 12 over time. It said 3 seconds have passed. So negative 12 over 3. The average velocity here is negative 4 meters per second. All right, so position versus time graphs are helpful because they allow us to not only visualize the motion, but in some cases to actually calculate the speed or velocity. And that brings us to this point. If you look at this position versus time graph for 3 different people, let's say, we have green, red, and blue representing the 3 people. What's different about their motion in this part? They're the same at the beginning, but then they split up. What's different about these 3? If you look at the red one as our standard, the green one is going the same change in position. They're all 3 going in the same position change here, but it does it in a much shorter amount of time, a very quick time. So this is a very fast person. We'll say this is our medium. And then this one takes a long time to go that same distance. So this is a slower person. So we have 3 different speeds represented here. And the language we use to describe how steep of a climb they go on the graph is the slope. And so the steepness of the slope reveals the speed of the object. And it's really cool, too, if you know the formula for the slope of a line, it's rise over run. Well, if we, instead of using the words rise over run, if we talk about, well, what is the rise representing in this case? Look at the axis over here. This is the x-axis. It's the position. And so the rise would be how much it goes up or down, right? The change in the position. And you remember the symbol we use for that? Change in position is delta x. And we're including the direction here. So delta x is the rise or the change in position. The run is how much you go across left and right. And that's represented by the time, the change in the time, which we always measure time as the change in the time, how much time has passed. So we don't have to write delta. You can. Some people do, but we can just write t. Now that should look familiar. Delta x over t. Well, this is exactly equal to the average velocity. So if you include the direction in your slope, then the slope of a position versus time graph is the average velocity of the object. If you calculate the slope, you have calculated the velocity. That's why these are so helpful. Let's look at a few other examples of this just to drive the point home. I've got a position versus time graph here. There are three different kinds of slopes appearing in this graph. We've got some places where the slope is 0. Where there's 0 slope, the line is horizontal, and that means there's no motion. If the line is ever moving up and to the right at all, then we call that a positive slope, and that just means that the motion of the object is in the positive direction. So in that phrase, we mean typically it's moving to the right, or it's moving up, or it's moving north or east. There's different ways we can define what the positive direction means, but that's typically what we mean by that. So in this graph, we have positive happening here, and that's it. Here we have 0 and 0, and there's another 0 and another 0. And then finally we have negative slope, and that's when the motion is in the negative direction, which sounds scary, but really it just means opposite of the positive. So that could be to the left or down or south or west or anything like that. So we have some negative slopes right here and right here. They're just moving this way, down and to the right. Remember, time is always moving forward, so we're always reading these graphs from left to right. So if it's moving up, then it's going in the positive direction, and if it's moving down as you move to the right, it's going in the negative direction. One more example. What if the slope looks something like this, where the line is not straight, it's actually curved? Well, in that case, all it's telling us is that if the slope is getting steeper, like it's continuing to get steeper and steeper, that just means that the object is getting faster and faster. So this object right here starts out pretty slow, moving in the negative direction. Maybe it's falling, so it's going slow. But as it continues to fall, it starts to gain a little more speed, and the slope gets a little steeper and steeper and steeper until eventually it's moving very fast. So this is an example of an object speeding up if the slope is getting steeper. We could also draw the same line but going the other direction like this, where it's starting out slow, 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 and then faster. Right? Either way, it's telling us the object is getting faster. Over here, if the slope is getting less steep, let's say it starts out really steep, but then it gets less and less and less and less steep, then that's the opposite. The object is slowing down. And so this object is going very fast in the negative direction, maybe to the left, and then it's slowing down, still moving left, but it's getting slower and slower and slower. So hopefully that helps to show you the different ways we use position versus time graphs in physics. That's all I've got for you in this video. Remember, everything you have is a gift.